problem now on the capacitance. This is kind of an interesting type of situation. You're basically going to have, you're going to take a capacitor and you're going to initially charge it with a battery, and then you're going to disconnect it from the battery and then connect it with some other capacitors. And the question is going to say, what's going to happen to the system? These kinds of problems always kind of take students by surprise because there's no external battery in the system. So let's assume that the capacitor is initially 3 microfarads, okay, and you have a 10-volt battery, and you connect it to a capacitor that's 3 microfarads, and you wait till it's fully charged. Then you take that 3 microfarad capacitor and you connect it to 2 other capacitors in parallel, let's say a 4 and a 6 microfarad capacitor. What's going to happen? What's the voltage of each? Tell me what the voltage of each is, what the energy of each is, what the charge of each is. How is that charge going to redistribute itself? So here's the argument that you make. You say, well, the 10-volt battery gives this a certain charge. Q is equal to CV, okay? So 3 microfarads times 10, 30 microcoulombs. So right now this has 30 microcoulombs of charge. And how much energy is stored there? Potential energy, initial we can call that. Half CV squared. So half times 3 times voltage squared. So you're going to have 1.5 times 100, 150 microjoules. So I have now stored 150 microjoules of energy there. So now I disconnect the battery, take the 3 microfarad capacitor, connect it in parallel across these. This capacitor starts giving charge to this one and to that one, and the voltage of the initial voltage of the 3 microfarad capacitor starts to go down, go down, go down, until the voltage of these two, of all of them, must be the same, until they stop. And then that causes the system to come to equilibrium. So here's what we're going to do. These two capacitors here are in parallel. So find the net capacitance of those two, okay? This is, I'm going to put the 3 microfarad capacitor in, just rewrite that. What's the net capacitance of 2 parallel? You just add them, right? You get 10 microfarads, okay? So now here's what you argue. The charge of this goes down to equal to some charge Q1. It loses some charge. The charge of this guy goes up or up. Let's call that Q2. Okay. This one stops giving charge to that until the moment when the 2 voltages are equal to each other, and then it stops giving charge to the second capacitor. So the voltage here, remember, V is equal to Q over C, right? So the voltage here, V1, is equal to Q1 over C1, so it's equal to Q1 over 3. The voltage there must be equal to that. So it's equal to V2, which is equal to Q2 over 10. Okay? So what do we have so far? We have Q1 over 3 must be equal to Q2 over 10. Now what else do we know? The sum of the 2 charges must be equal to the original charge. You can't create more charge out of nowhere. The original charge of the capacitor was 30 microcoulombs. So the 2 must be equal to that, the sum of the 2. Okay, so now we can multiply them. Okay, then put here 10 Q1 equals 3 Q2. Q1 is equal to 30 minus Q2. Then you have 300 is equal to 13 Q2. Okay, and then Q2 comes out to be 300 divided by 13, which is 23.077 microcoulombs. So the charge of this guy here is 23.077 microcoulombs. The charge of Q1 is equal to 3/10 of that. Or you could say it's equal to 30 minus that. So 30 minus that, it's going to be 6.923 microcoulombs. So now let's solve for the voltage across each, which should be equal. V1 is equal to Q1 over 3. Divide this by 3. 2.308 volts. And V2 must be equal to Q2 over 10, which is this thing, so 2.308. There's some rounding error and stuff, but it should eventually be equal to each other, and they're going to equal the same voltage. Now, what's going to happen to the original, my 4 and 6 microcoulomb? Well, whatever voltage is here is also going to equal that, right? So this is going to also be the same voltage, 2.308. This is also 2.308. This is also 2.308. So if I want to know how much charge this has and how much charge this has, well, charge equals C times V, so you multiply the two. Q is equal to 4 times 2.308. That's equal to 9.232, and the charge of this guy is going to be, this is Q of the 4, this is Q of the 6, and that's going to be 6 times 2.308, 13.848. Okay? Now, if you add the two charges, what should they equal? They should equal the Q2 that we found, right? 13.8 plus 9.2, it's going to equal 23, which is the charge of the combined 4 and the 6. This guy, okay? This is 23.077. And they are equal. If you add them, it's going to work out. 13.8 plus 9.232 with some rounding error comes out 23.08. Okay, now we know what the voltage is, we know what the charge is. Let's find the energy. The initial energy stored in the capacitor is 150 microjoules. How much energy is stored here? Okay, so let's just calculate here. Potential energy total, okay, is half C1 V1 squared plus half C2 V2 squared plus half C3 V3 squared. We could do that version if we want. Now C1 is equal to this capacitor. Actually, they're all the same voltage. Voltage, voltage, voltage. It's equal to a voltage of 2.308. So you can just say half, add their capacitance, since they're all the voltage is the same. And if you add their capacitance is 6 plus 4 plus 3, that's 13, right? Times the voltage is 2.308 squared. Okay, so that's going to give you 34.625 microjoules. Okay, so the energy has gone down quite a bit.